Hello and welcome to the fourth lecture of CS6650. Today we'll be covering some programming aspects of ATmega 328P microcontroller. And before we start looking into the programming per se, this is an overall picture of the different aspects about the microcontroller architecture that we have covered in the last couple of classes. So if you remember, we started with understanding how a program is executed in the CPU. So this is where the programs are executed, and the binary of the program is loaded from the application section in the flash memory, right? And we remember how we studied about the instruction decoding, the how the operands are fetched, right? And then it is executed. And we also had this bootloader, which is a resident program inside the flash memory. In one partition, there is this bootloader, which is responsible for fetching the program from an external computer, right? It could be another microcontroller, or it could be your laptop or desktop, from where the program binary is actually fetched and then written to the application section of the flash memory, whatever is the resident application in our microcontroller application. Okay. And we also discussed about the SRAM, where the program does the all the bookkeeping tasks, right? The program stack is here, as well as all the free memory. The variables that we declare are all stored at runtime in this memory. So all this runtime job related data is stored in the static RAM. Right, and then we also discussed about the CPU registers and the IO, the input output registers that could be used for interfacing different peripherals, things like counters, how they can be controlled, and we can also interface digital sensors. And for that, we have this two-wire interface of the I2C bus as well as the SPI bus and so on. So all of them, these different peripherals, are all connected to the CPU using this memory called the register files and the IO. And we also discussed about the clock as well as the concept of prescaler, how the clock is downsampled and fed to different peripherals, right? So the prescaler is something that we also discussed in the last class. So different peripherals have maximum clock rate that it can support, and based on that the prescaler is decided. So this is an overall picture of the microcontroller architecture. But yeah, if you want to get more details, you should consult some course on computer architecture if you want to know more details, right? We just covered something which is really simple to give an overall idea, right? Before delving on to developing code for these embedded systems, you should have some idea about what are the different types of memories, how is a program executed, what is a program counter, and so on. So as long as you know them, you would be at least comfortable in understanding, right, to in your code. So today we will mostly talk about the application development, right? How we write our own code. So this is our own uh, application software, right, that we intend to run on the microcontroller hardware. So on the lowest level, we have the microcontroller hardware, right? So we write it mu C, and this is sort of the interface in between the software, the lowest level software that is directly running on the hardware, right? So and we have a series of abstractions on top of the software, right? So we have these abstractions that is added on top of the lowest level of the software. We often call this bare metal, right? The bare metal program, right? That is running with direct access to the underlying hardware. So there is no more APIs or no libraries that is going to help you write the program. So this program at the lowest level is directly written uh, for the specific hardware, right? That specific machine. And with these abstractions, you basically develop a series of these application programming interfaces or APIs that gives you some sort of a quick access to the underlying hardware without having to bother much about the implementation details, right? Let's say your hardware has an access to an LED, right? So suppose there is an LED here, right? LED. So, and in your application software, you might have access to an API called turn on LED, right? Turn on some underscore LED, let's say. Right, so this is an API, and all you have to do from your application software is to call this function. Right, if you call this function, all these complicated things happen, right, which eventually helps in turning on this LED. Right, so there could be certain amount of memory that is has to be accessed, and that has to be written, right, by the device driver, which in turn actually helps you to turn on the LED. But from an application standpoint, you don't have to bother much about that, right? So how? Because the series of APIs that has been developed and all the intermediate libraries, right, take care of that. Okay. Okay. So now let's start with an Arduino program, and these Arduino programs are called sketches. And on the left hand side, I just show the bare skeleton of an empty Arduino sketch. Right, this is an empty Arduino sketch that does nothing. Right, but these are the two functions that has to be defined inside an Arduino sketch at the minimum. Right, so one is called setup, and the other one is called loop. So what is setup? Setup is something that is called only once, right? Once you start the program, right? Suppose your application program is already loaded in the flash memory, and your microcontroller is restarted. So once the program is like when the microcontroller hardware is restarted, it will start executing this sketch, right? And as a part of that, it will initially execute the setup part of the function. So normally this will be used to do the initial configurations, right? Initial some declarations or some initializations you have to do, some initial configuration. These are the things that are done only one time, and later there is another function called the loop that is repeated. It's like an infinite while loop. So if you want to do something again and again, that will be content inside this loop function. Let's suppose you want to keep on sensing temperature, and based on that value, suppose you want to display the value of the temperature in a screen, right? And this is an infinitely for an indefinite long amount of time, you are just going to do that, right? So there is no end to your program unless and until somebody comes and switches off the hardware. So most of the microcontroller based applications will be like that, right? There is a definite job that you want to keep on executing, right? It's not that compute intensive, right? Suppose I give you a lot of data and then ask you to do some processing. So those kind of things are not really done in these scenarios, right? Wherever you have these IoT applications deployed, most of them will be perpetually running, right? Doing some kind of a task. So there is a certain task that will be repeated uh, indefinitely, right? So on the right hand side, I show you this empty sketch in the Arduino IDE. So most of you, if you have already gotten hold of an Arduino device, right, and you have installed the IDE, I think you have already you'd be familiar with this screen. So on the left thing, right, the tick mark is going to compile your code, and this is going to uh, upload the code and flash it in their flash memory. So this is going to send the program to the flash memory. Okay, of Arduino. So if you see on the bottom, it says that this is verifying the program, and then it's actually uploaded after that. Okay, so now we will start with a I would say a customary program called Blink. It's a very common program. Anybody who is taking a course on Arduino, right? They will first introduce this as a first kind of introduction, uh, introductory program, right? The way we write a hello world program in C or Java, whenever you are introduced to a programming language in a computer, right? We do write this kind of a print program. So in the same way, we don't have a console that is attached to this Arduino device. The only input output pins are the medium of communication to the device, right? So if you want the code uh, to do something that is visible from the outside world, we can, very simple thing we can do is that we can turn on and turn off an LED from the program, right? So pin 13 is one of the pins in the board that is marked here. So I'm marking this. So we attach LED, right, to this digital input output pin 13 for example here. And one good thing is that this Arduino already has an LED that is attached to pin 13, so you don't have to put an external LED. So this external LED is just for demonstration. In an Arduino board, if you happen to have one, pin 13 is already attached to an LED that is on resident on the board itself. So if you want to turn on that LED, you have to turn on that pin number 13, right? But there are ways to do that. That's what we are going to see. So what we are trying to do is we need to blink the LED at a predetermined duty cycle, which means that for certain amount of time, the LED will be on, and for some time it is going to be on, and then it's going to turn off, and it is going to remain off for some amount of time. Then again, it is going to turn on, and it is going to continue, right? So there is an off period, right? This is off. So there is an off period of time, let's say t1, and then there is an on period of time t2, right? So these are the two different times. So in this case, we have taken this both of them as 1 second. So we have to turn on that pin number 13, wait for a second, then turn off that pin number 13, and then again wait for a second, and this is going to continue, right? So as you see, before doing all these things, we need to configure this pin 13 as an output, right? So these are digital input output pins. They can either be used as an input or can be used as an output. So we need to make sure that this pin number 13 is configured as an output, and this is a configuration that is not going to happen every now and then, right? With every iteration of the loop, you don't need this. You can do this, but it's not needed, right? So this thing can go to the setup part, right? So the setup function, if you recall, is executed only once in the beginning, right? It's not again executed after that. And this task is going to be repeated over and over again. So this can go to the function called loop. So inside this loop function, we can write the necessary code that is going to emulate this thing, right? Turn on this LED and then introduce a delay to wait for a second, turn off, and then again wait and repeat that process, right? It's like an while loop. Okay. So as I said, we are writing a high level code, and we have to take help of the underlying libraries and the APIs that are provided. So what we can do is all these things that I have written on the left hand side as the flow chart, this translates to a certain APIs that are provided as a part of this Arduino libraries, right? So the first thing that I'm going to bring your attention to is something called pin mode. So this is a function which determines for a certain pin whether it will be used as an input or an output. So a digital pin, let's say it has the pin number is n, whether this is going to be an input pin, it is going to receive certain digital signal, or it's going to be used as an output, right? Like whatever is going to be like from the program itself, we can output a certain thing in that pin, right? Whether we want to make it high or low, that is our choice, but we can configure that pin to output certain thing from our code. Okay, so for that we need this API called pin mode, and it takes these two arguments. The first one is the pin number, and the second one is whether we want to use it as an input or an output. Okay, the next thing is another API called digital write. So digital write is like, because it is configured as an output pin, now we can either write 0 or 1. So the first argument that we provide here is again the pin number, which pin we want to write high. But before that, before writing, I have to configure this particular pin as an output, right? If it is not configured as an output, if it is configured, let's say, as an input, this is not going to work, right? You have to make sure that that pin number 13 is actually configured as an output, and then only we can put the output as either a high or low, right? So in this case, we have put an output, we are trying to write this value high or 1 in this digital write function. Next is we apply another API which is going to introduce some delay. So after turning on that LED or writing 1 to the pin number 13, the CPU is going to wait for 1000 milliseconds. So this is taking an argument in the units of milliseconds. So 1000 millisecond makes 1 second. So your pin number 13 will be high for 1 second, and then we are going to make it low, and again have introduce a delay of 1 second. So your final output will be something like that. 1 second it will be off, 1 second it will be on, again another second it will be off, another second it will be on, and so on, right? And since an LED is connected to pin number 13, and high corresponds to higher voltage, right, or a logic 1, this is going to light up the LED. So in effect, you are going to see the LED blinking. So it is going to turn on and turn off. Okay, so hope this is clear. How to use these APIs, right? We are basically trying to see that from the high level application code, like this we have many other APIs. So this is a very common example that I have given, and we are going to come across more and more examples as we explore other sensing scenarios, right? This is a starting point where I'm trying to introduce the basic coding blocks, right? And even complex things that might come up with a simple example like blink today, and later we are going to look at many other different APIs, right? So here today we'll just stick to these three APIs, right? One is pin mode, one is digital write, and the other one is delay, right? And we can see how deep we can go inside this particular APIs to get a clearer understanding of what is going on under the hood. Okay, so this is the actual program, and as I told you, you can simply run this program, right? If you have an Arduino at your disposal, you can simply run this program and see what is going on. And LED built-in is nothing but a macro. It just says that it is going to turn on the LED that is built in on the device itself, which is connected to pin number 13. Okay, so I would request all of you to at least try out this program and then see that all your configuration and settings are correct and you are able to run that without any errors, right? And on the bottom side, you can get all these compiler messages. So here we are getting that 9084 bytes of flash. So the program binary size is 924 bytes that got uploaded into the flash memory, right, application section of the flash memory. So now we are going to revisit how this digital input output pins are manipulated, but before that we'll take a small detour uh, and again come back to that quickly, right? So um, we remember from last class, right, when we talked about this memory architecture, is we had this SRAM, but before we start storing the program data, there are some other things that is also used, right? So one is this general purpose registers. There are 32 general purpose registers. There are 64 input output registers, and then there is 160 external input output registers. So the initial part of the SRAM before my program memory starts, they have this 256 bytes of memory, that chunk that is actually dedicated for registers or special part. They might have some special purpose for input outputs, and there is a 32 general purpose registers which can be used for computation, right? And after that we have this internal SRAM where all this declared variables or the program bookkeeping takes place. So if you declare a variable in your code like this character I is equal to 69, this will be stored in the beginning of the SRAM where your registers end, right? So this is from 00 to 256. So FF is 256. After this is done, you are going to store the next byte after that. But if you want to store it inside a register, which is nothing but it's a reserved or predefined byte space in your data memory that has a special purpose for the microcontroller, and we will see why, right? So if you just simply declare a character in your character I, here this I is a variable in your program, it is just going to be simply stored in your SRAM part, which is not including this previous registers that we spoke about, right? However, if you want to put it in a very something in one of these previous 256 registers, right, wherever you were allowed to write, some of them are reserved as you have seen in the last class. So wherever you are allowed to write, you can write a particular value there, right? Let's say we choose this address of 0x2b, right, 0x2b, and in that particular address we want to store the value 69. So where is 0x2b? So this is definitely after 1f. So this is skipping this 32 registers. It is not here. And then we are definitely entering this next zone where we have the 64 input output registers. And as we see, it starts from 0x20, which is 32. And then it continues till 5f, right? What is 5f? 96, right? 5 into 16 plus 16, right? So we have 32 here, we have 64 here, so till here we have 96 bytes, right? And here we are choosing this 2b, which is somewhere in the middle of the 64 registers. Okay, so now all these registers, as we have seen in the last class, has some special purpose, right? These are not random memory locations where we can just go ahead and store data, right? So they mean something, right? Either in terms of input output or in terms of certain internal peripherals like the ADC we have seen or the timers. They are going to serve as configuration to these entities, right? So in this case, if we choose this location 0x2b, it happens to be a register called port D data register, right? Later we are going to see what it exactly means, right? But this is a register and that has a special purpose, right? What is port D and all, we are going to see very soon. So you can see the address of the register as 0x2b. It is written here, and then there are some meanings, as you see, right? Every bit in the port D data register means something, right? There is something called port D 1, port D 0, and then till port D7, right? And you can either read or write a value, write a bit here. So all of these are bits, right? This is a register of size 8 bits or 1 byte, and every bit has some meaning, and this bit could be set or reset, read or write. Okay. Okay, it's clear. So now what this port D data register means in the context of an Arduino is this. So this port D register is very special because based on the bits that are set or unset inside the port D register, we can turn on or turn off a certain digital input output pin. Right, if you look at an Arduino board, on the right hand side towards the in the lower right hand side, you will see these pins starting from 0 to 7. So you will see this digital input output is written here, digital, starting from 0. So 0, then 1, and dot 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 up to 7. So there are these 8 pins here, right? And what is interesting about this port D data register is that all these pins could be directly controlled by on the basis of the bits that has been set or unset in this port D register. So we have set the value of the port D register as 69 because we have said that the value that we write in the 0x2b memory location is 69, which is nothing but this binary value. So 69 in binary form, right, is this, right? So one is this has the place value of 64, and this 101 is 5. So 64 plus 5 is 69. So this actually sets bit 0. So the 0th pin, if you attach, let's say, an LED to the pin number 0, this should turn on, given that we want to use this pins, all of these pins as a data output, right? As we have seen, like pin mode for pin number 0 has to be output, and the same holds true for the other ones, right? So 1 is off, 2, 3, 4, 5 is off, and this is 6, right? So see how this memory locations, particularly these input output registers, the value you write in them can be actually used to manipulate the pins, right? The way we were doing using this digital write, this is trying to achieve the same function, or this is how it is actually implemented underneath, right? And we will see in a short while why this is sort of important to understand. Okay, so within Arduino, we have this nicely laid out collection of ports. So we have this port B, which is a collection of 0 to 5. So there are 6 input output pins. There is this port C, which is again there are 6 input output lines, and port D that has PD0 to PD7, 8 input output lines. Okay, and on the left hand side you can see the corresponding Atmega 328 pins, right? So some of these pins have multiple functionalities. For example, if you see pin number 27 and 28, they belong to port C. They can be used to do digital input output, right? You can turn on an LED, or you can have this input go to a speaker, right? And or you can actually generate a signal using these 2 pins. And at the same time it can be also used for I2C, right? So this is the serial clock and serial data which could be used to interface some kind of an I2C bus enabled sensor. So we need to be careful, right? If we are using this I2C bus, we cannot use this pins for doing some kind of a digital output. We have to use some other pins. So there is this multiplexing that goes on because we have limited number of pins in the package, but they have tried to put as much functionality as possible inside the microcontroller, right? So you have to be very judicious in terms of the pins that we are trying to use for a certain application. Okay, and the other takeaway point here is that all these pins, at least for the general input output, right, GPIO, the general purpose input output, they are organized into these 3 ports, port B, port C, and port D. So this basically refers to a collection of the output or input pins, right? Once you talk, if you do some kind of configuration changes in port D, that can apply only to this set of pins, right? So, and in an Arduino board, they are sort of nicely reorganized together, right? The port D, all these pins are together. Port B, all these pins are like successively one after the other, right? And same for port C. So now we have already written this program and ran this program for writing a high or a low value to a given input output pin, and we have seen it work, right? If you happen to have this, please try to run and see that it is actually working, right? So what is this digital write API is being used for? Setting a specific bit in a register that controls a specific pin, right? So we have seen this example of this port D data register, and we were seeing that setting a particular bit in this port D data register is turning on or turning off depending on whether it is set or reset a given pin, right? So some bit in a port D data register is responsible for controlling the input output behavior of the set of pins in a given port. Now what we can simply do is, by the way, so since we are dealing with this built-in LED, which happens to be pin number 13 in case of Arduino, so this happens to be port number B, right? So we are dealing with the built-in LED. So this is pin number 13, which is PB5, right? You have to remember like this. So PB5 is the fifth bit in the port B register, right? So port B is one port, and then every port, as you will see, has three registers for controlling the input output nature and what data has to be set there, right? Just for now, remember that we are dealing with pin number 13, and pin number 13 can be controlled by port B. Port C and port D are not responsible for controlling pin number 13's digital IO behavior, right? And that too, port 13 is sorry, the pin 13 is corresponding to the fifth bit, right, in while dealing with this port B registers. So 8 corresponds to PB0, 9 corresponds to PB1, 10 corresponds to PB2, and so on like that. 13 corresponds to PB5. So more about the GPI programmability we will discuss now. So see, if we look at port B, just now we have mentioned it's very similar to the port D register. It is the port B data register, and based on whatever value is being set. So in this case, as I said, we were setting the value of the port B fifth bit, right? So we are turning this value to 1. What will happen? So this particular pin corresponds to the Arduino pin 13, and if you set it 1, the LED will be on, right? So, and the rest of them could be zeros. So we have these are zeros, so 0 0 0 0, and then we have all zeros here, 0 0 0 0, and this fifth bit could be either 0 or 1. So if it is 0, then we can write port B is equal to 0, which means pin number 13 will be off. And if it is 1, that is basically 32 in the decimal system. Here you can, in the hexadecimal system, it will be 0x2, and we are getting a 1 0 from here, this 4 bits, so 0. So it's basically 0x20, which is nothing but 32 in the decimal system. So we say that port B is equal to 32, which turns on the fifth bit in the port B data register, which is controlling the pin number 13, or it's basically controlling the whole port B, and out of that we are interested in the fifth bit because it is controlling pin number 13. I hope this is clear, right? This is how from the register itself we can control the GPIO pins. Okay, so this gives us a little bit one layer lower control, right? Rather than using the APIs directly, we are trying to do it ourselves instead of using their API, and that has some serious reasons why we want to do like that. Okay, So that is exactly the question that I was asking. Why do we care, right? So we wrote these two programs side by side. On the right hand side, we are using this Arduino API for digital write, and on the left hand side we are not using anything like digital write. We are directly manipulating the value of the register, right? The port B register, there is a address that we will see soon. That particular memory location is being written as 32 and 0 successively, right? And note that there is no delay. We have not introduced any artificial delay in the code, which means that if you have this Arduino device, let's say this is the Arduino device, and we have this pin number 13. So this is, let's say, pin number 13, and we connect an oscilloscope, right, to this, which is going to give you a visualization of the uh, how frequently this switching is happening, right, in pin number 13. So what is the intended behavior? The intended behavior of pin number 13 is it's going to go high and it is going to go low, and it is going to go high and this is going to go low, right? And what will be the speed of this operation? This will be comparable to the CPU clock, right? Higher the CPU clock is, more faster, right? Faster we are going to switch the high and low values in the pin, right? So this will be fast, right? The way or the rate at which it changes, right? This has to be fast, right? And this is a function of the CPU clock, right? So uh, how frequently we are switching this, right? If there is no other overhead, because there is, in the code we did not introduce any other overhead. So if we actually attach an oscilloscope here, you can see the output in the following, right? So as you are observing on the left hand side, we can see the frequency at which this pulse gets created is something like 2.78 megahertz, right? I'll just use a different color to highlight, right? So if you actually attach an oscilloscope to pin number 13 with this program loaded, port B is equal to 32 and port B is equal to 0, the switching happens so fast. Whereas if you attach, if you burn this code with the version where we have these APIs, where digital is doing the same job but using APIs, right? So the maximum that you can do is 148 kilohertz, right, which is approximately 19 times lower, right? Without doing anything, right? Just using the raw register manipulation instead of using a digital write API, the typical function call that we use in most of the Arduino programs. You see that there is a huge overhead if we try to use these APIs, right? So this is something like an eye opener. So if you want to create a waveform, right, later for many sensing applications, right, we often need to create something like a pulse, right? Some kind of a square wave or something, right, we want to generate. And let's say we want to generate this pulse at 500 kilohertz, right? This will be impossible if we are trying to use these APIs, but the hardware is capable to do that, right? Your software overhead is so much that your hardware is not able to achieve that particular desired rate, right? Whereas we can easily receive something in the order of 2 megahertz, right, from the same hardware, right, using the same hardware but not using this series of abstractions and APIs. We can do it much faster. So this is an argument against why you should slowly start avoiding the high level function calls if you want to build something that runs in real time and uh, does the job much more efficiently. Not only that, in terms of size also, right? If you see, 924 bytes of memory was used in the first case wherever we were using these APIs, right? Whereas we were only doing it in 756 bytes if we are using this kind of a program, this kind of a statement. Okay, so it's already saving you 19 times the speed. It's becoming 19 times faster and 18 times in 18% in terms of space. So we need to summarize this, right? So if we want to control this input output pins, right, which is a very common feature for many sensor based applications, when we try to interface or pass certain signal to different IO input output devices, basically there are three ports that we have to be aware of, right? So three registers, sorry. So each port, we have already mentioned that we have these three ports B, C and D. So for every port, uh, we basically, there are three registers. There is a DD register, there is a port register, and there is a pin register. Right? And within the register, there are 8 bits. So every bit corresponds to a certain pin in that particular port. Yeah. So there is a DD register. We will explain the meaning shortly. There is a port register and there is a pin register. So this happens for all ports. So B, C and D. Same for this B, C and D, and same for this one B, C and D. So you have basically three DD registers, three port registers, and three pin registers, and each register will have 8 bits, right? This will have 8 bits, this will have 8 bits, this will have 8 bits, right? And each bit will be controlling a certain aspect of that pin, right? So if it is port B, if it is port B and we are basically looking at the third bit here, so it is going to do something with the third pin in the B port. Okay, so this is just a summary about what they do. So port B, as we have already introduced, is directly controlling that what data is being written, right? Whether it is high or low. Based on that, a particular output or input pin will be this input output pin will be set as high, right? So whenever we try to do an output, actually, so as we saw in the LED example, we were trying to turn on this pin number 13, which was corresponding to this bit 5 of port B register. So if we turn on this particular bit, if we write 1 here, this is going to turn on the corresponding pin, right? And before doing that, we also mentioned that it has to be configured as a output register, right? It's had to be configured as an output pin, right? So remember the API that we were using, pin mode. So in the very beginning, we are using this thing pin mode 13, and we are giving something like output, right? So 13 is basically a port B register, and the way we are controlling this particular pin mode is called data direction register. So the data direction register determines whether we are going to use that particular pin as an input or it is going to be used as an output. So in our case, this is only one time declaration that we are trying to say that pin 13 will be used for an output. So how do you know which particular bit? So once we say this pin number 13 in Arduino, this basically maps to port B, and which pin inside port B? This is the PB5. Okay, so these things are available in any sort of manual, right? And PB5 is basically the 5th bit in the DDRB register. So if we actually know the address of DDRB register, which happens to be 0x24, so in this memory location, if we write this value where all these bits are zeros and this is 1, this will configure this particular pin number 13 as a for output. Okay, and once it is configured as output, we can write any value that we feel like using the port B register, port B data register, right? And similarly, this pin B register will also be used if it's going to be used as an input pin, right? Currently we are using it as an output pin, but it could also be used as an input pin. For that, you cannot write anything. Only thing that you have to do from this particular pins is just to read, right? So W is not there, please note, only R. So you have to only read a value from that particular pin, that is either high or low, which is typically put forward by some other peripheral from outside. So now we know the meaning of this data direction register. So we are using this only once. So DDRB is equal to 32, right? And then apart from that, we also are setting the value of port B successively 32 and 0, and with a gap of 1000 millisecond or 1 second. So there is a 1 second sleep sort of, or it's not a sleep, but it's like a busy wait. It's kind of executing something that to make that delay happen. So for simplicity, we will write, let's say, 1 second sleep, and then again there is a port B is set to 0, which basically turns on and turn off this particular bit, right? So this is the only bit that is repeatedly getting overwritten, right? So it is 1, then it is 0, this is 1 to 1, and again it is going to be 0. So it keeps on rotating like this. And for the data direction register, this is a one-time job. We have written this particular bit as 1, right? So this is we do in the setup code, and this is what we change in the loop part of the code. Okay, I hope this is clear. And now we actually save a lot of space, right? We removed pin mode API call. We have removed this digital write API call, and just by replacing this API calls, we have already seen that the program is much more faster, right? The extra overhead because coming because of this libraries was slowing it down. And other thing is that the code also shrinked by 30%, right? Instead of 924 bytes for the simple program, we now end up with 646 bytes. So what can you do about delay, right? So one idea is that we just do a busy wait, right? We take a variable I and increment the value of I till we reach 10 to the power 6. So we count for 1 million times. So we increment the value of I a million times, and that indirectly will introduce a delay. So that delay corresponds to something like a 1 second sleep here. So you're trying to simulate that delay by doing some kind of a busy wait, right? So you have gotten rid of the delay function call. So you are using this API, right? So instead of that, we have written our own hacky version of delay, which is just going to keep the processor busy for a certain amount of time, right? So based on the clock speed, we have chosen a value of 1 million, which will give you an approximate delay of 1 second. Okay, so now from the 30% saving, we are saving even more space. So from 924 bytes, it has shrunk to 456 bytes with 51% space saving. But the problem is that it doesn't work, right? And the reason it doesn't work is because of the compiler, right? So the culprit here is the compiler. What the compiler thinks is this particular code fragment, both the for loops, they think that this is kind of useless, right? There is no useful work that is being done, no useful work that is being done in the code. So the compiler thinks that let's not keep the code fragment because it's just a waste of your memory, right? In the application binary, we don't want to have this, right? There is this variable and this is being incremented, and there is some real estate in your memory space that will be wasted for not doing any useful work. So the compiler optimization is going to kick in, and this will be removed from the code. Both these lines will be actually removed from the code, right, which is going to destroy the functionality that you needed, right? You wanted to have this delay, which is no longer be available now. Okay, so one way to kind of trick the compiler is to tell that it is doing something useful, whereas you don't do anything useful, right? Don't do any extra operation. So something called no operation. So in this is basically an assembly level code. So you can, in the C program itself, in the sketch, for example, you can actually pass assembly level instructions, right? And once we discussed about this instructions without any operands, we mentioned this NOP, right? No operation. That sleep is one example where you have this opcode and there is no operand present, right? Uh, like that, this NOP is also another assembly level instruction in the AVR architecture, where it doesn't do really anything, right? So although it is an instruction, the instruction doesn't do anything, but to the compiler, it they will think that okay, at least it contains some assembly level code, right? So at the high level, it's not going to see what exactly is inside it, right? So it is not going to eliminate the for loop directly. So it will keep the for loop, and then when the assembly level instruction is there, this will be replaced by this NOP, which is not going to execute any extra stuff, right, to make the program artificially slower. Okay, so you can see that by doing this, this is a working code, and this will be saving you about 50% of space, right? So from 924 bytes, we slowly came down to 490 bytes by shrinking the code size, right, by not using the APIs and the library functions. So now you can see the stark amount of improvement that you can bring to a very simple code like blink, right? Just blinking an LED. There is no fancy thing it is doing. In a simple code like this, we are able to do so much of improvement, right? And you can always use this GCC optimization flag. They are really useful sometimes if you mistakenly do something where you did not pay attention, right? Some part of the code could have been optimized. So in that case, you can always turn on this optimization flag. So you can look at the GCC manual, try to see that what are the different possible options for this optimization flag, and using 0 will turn off the optimization. So now we have covered, we were directly using this macro sort of thing where we were mentioning port B is equal to 32, or we are using this DDRB, right? We are using the names of the register is equal to 32. This was either 32 or 0, right? We can also use the address. Just if instead of using the name, you can directly use the address, and that will, if you do that, it will give you more confidence, right? Just by using the address, you can directly manipulate those registers, right? So there are two addresses for somehow, we are going to see that later. It's a strange reason why there are two addresses for the same register. It does actually address the same register, but somehow there are two addresses, 0x05 and 0x25, right? It should have only one address. We'll see why. So one quick way to replace this DDRB, if you want to really get rid of these macros and really understand what is going on, because DDRB is not defined here, it will be defined in some other header files, which will take care about the pin to port mappings. So if you don't want to depend on that and try to write this code directly dependent on the addresses, right? In the manual sheet, you already know what addresses you want to manipulate, right? So if you see DDRB, so DDRB has this address of hexadecimal 24. So we can take a byte pointer and define the value of that byte pointer as hexadecimal 24, and then the value at that particular address we can write 32, right? So this is same as writing byte star ddrb is equal to 0x24, and we are writing star of ddrb pb5. So this is the variable name that I have given is 32, right? So please note that while we do operate on memory, right, it's a good practice to use this modifier or like qualifier volatile, right, whenever we declare a variable, right, because there could be many operations in the hardware that is changing the value, right, and we don't want the compiler to do any sort of take any decisions on its own, right, whether to update that particular variable or not, right? So whatever updates will be coming to that particular variable, we have to write that, right? So if you want a little bit more explanation on volatile, I could refer some materials so that you really know that how to use this volatile qualifier while programming embedded systems, right? If you don't do it properly, right, certain updates could be lost, right? This is quite important. In our case, it might not matter a whole lot, but it is a good practice to use this volatile qualifier, right? In cases where you are directly dealing with the memory locations, and it could be converted to a one-liner. So this is the volatile byte star is the pointer, and this is the address, and this is basically saying that the value at, right? So the value at that pointer location is being replaced by 0x20. This is 32, right, in the decimal system. So this is equivalent to ddrb is equal to 32. So you can write this in the same way, just that you will have a little bit more confidence in if you implement this code and get it running, right? So you'll have more clarity about how this registers are accessed and how do you really write data there, and how that modifies the different configurations of these pins. And the same we do for the port B register, right? The port B register has this address of 25, so we can do the same thing. Now the same thing could be repeated without using uh, this the way we did using the memory access in this form, right? We can directly use assembly level instructions, right? So the assembly level instructions could also be used to write a certain memory location, right? In this case, there is an instruction called SBI, which is called set bit immediate, right? So we'll explain why it doesn't work. So there is something called the set bit in the IO register. So there is an immediately it sets the value of 5, right? So there is uh, no kind of redirection. It's not going to read from a certain register or a certain memory location. So this is an immediate data that is being passed to this opcode, which is SBI, set bit in the IO register, an address of 24. So this is the address, right? And we are writing this value 5. So it sets a specified bit in the input output register. This instruction operates on the lower 32-bit register of addresses 0 to 31, and this 5 is the 5th bit. So if you see this B value of B is from 0 to 7, right, with the syntax of A comma B, where A is the address of the input output register and B is the what bit we want to set. So as we have seen here, as we are seeing here, right, in the port B, we are interested in setting the 5th bit. So we are saying that in the input output register, we are interested in setting the 5th bit. So this SBI 0 to hexadecimal 24 is the for the DDRB, and while we do the same thing for the port B register, this is again the 5th bit we are setting, right? And this is nothing but the exactly the opposite thing. We are clearing the 5th bit. So this is the clear bit. So instead of set bit, we are using a clear bit, and again the same location. Hexadecimal 25 is the address of the port B register, and 5 is basically instructing to clear off the fifth bit. So this will be set as 0, and once we are setting it, it will be set as 1. So that's what is happening, but somehow it doesn't work because there are some more details about how this input output register memories are actually manipulated, right? So this is sort of important, and this exactly follows from whatever we have been discussing so far. So earlier, as you have seen, this was working, right? So when we were using this value of 24 from the data memory space, this was working, whereas when we are using this assembly language instructions and passing the same address, right, it doesn't work whereas it was supposed to work, right? And now we have this mysterious looking two addresses that was given to this input output registers, right? So when you see this, all these addresses, right, of port B, port C, or even the data direction registers, they will always have these two addresses. So now the thing is that we have one set of address for accessing from the data space. So from the SRAM or from the program, that whenever we are using trying to access that register, we have to use this data space address which is mentioned in the parentheses. Whereas whenever we are trying to use that as an input output register and using some assembly language instruction for manipulating that, we have to use something like called this IO address. Okay, so if you remember, we are using this byte star address is equal to hexadecimal 25 that was being used from the program memory, that the data address, right? Whereas the assembly language program, that operand and opcode, whenever we are dealing with that, it cannot understand this address of 25 to manipulate this particular register. So there is a reason why it is done. So in order to efficiently map the input output registers with minimum number of bits for the instructions, the IO registers are renumbered with data memory addresses 0x20 becoming the IO address 00. So what is basically done is this particular base, right, that was the general purpose register, these are actually skipped. So the first input output register starts from here, which has an address of 0x20 because this is the next. So your first set of 32-bit registers ends in 0x1f, and the next input output register starts from 0x20, right? So instead of using for your input output manipulation, instead of using this first location as 0x20, this will be used as 0x00. Okay, and the way this is going to be continued, right, till the last one, which is 96 in hexadecimal, which is 0x5f. We have to again subtract this particular base. We have to subtract 0x20 from this, and we will get the other value. So why this is done? Because we are using the first 32 IO registers. This is being represented by only 5 bits, right? And the entire 64 can be represented by 6 bits. See, if we are using their data space memory addresses, it will go beyond 6 bits, right? So this is the first 32 here is actually 5 bits. Again, if we start from here, the first 32 will be represented by 5 bits, and if we go beyond 32 here, so at least we can do using 6 bits, right? But if you don't have this modification, you will require 7 bits, because in all it will run from 0 to 96. But now, since we have subtracted this base by 32 or 0x20, so now we have to represent not from 0 to 96, but this can be mapped from 0 to 64 because we have shifted the base by 32. So in that way you can represent all of it by 6 bits at the most, right, instead of using 7 bits, right? If we actually wanted to address from 32 here, so this will become like 33, let's say, or from 0 to 31, now this is 32 to 95, right? So we have to end up using 7 bits, right? Whereas we actually saved 1 bit, and this is somewhat important in optimizing the number of bits that are being used in this instructions, right? So that is how we can save 1 bit, and that is the optimization that is being done with this input output registers, because there are so many input output devices and peripherals that we need to connect. There's just 64 might not be sufficient, and on top of that we also have this external input output registers. So there is a small optimization that has been done, and we need to follow this instruction while we try to access these registers from using this input output assembly instructions, right? And you can look it up in the manual. There are this several input output instructions. So some of them are, there is something called in, there is something called out, or the set bit, right? You want to set a bit, clear a bit, and so on. There are some of these instructions which directly work on the input output register, but the operand of the register has to be passed by subtracting the base address, right? Whereas if you are directly accessing it from the data memory, you don't have to do that, right? You can directly use whatever offset starting from 00 to whatever is the byte location in the SRAM. You can use that. Okay, this is a little bit convoluted concept, but yeah, if you have a confusion with this, feel free to ask, right? In the Google Classroom, you can put a post, you can discuss over there. So this will be the correct value, right? Instead of using 0x24, we have to use 0x04, right? And same, so this was for manipulating the DDRB register, which from the data space, from the data memory space, will have an address of 0x24, whereas from the input output register scenario, if we are using this SBI, the set bit thing, to manipulate this input output registers, we have to use this 0x24 and then shift it in the other direction, in the opposite direction, by 0x20, which makes it 0x04, right? And same happens for the data register, the port B data register. Okay, so now we started with something like this API calls, right? And we've gone a long way and seeing that we are directly using assembly language, right? Which is assembly instructions. To do the same job, the job was pretty simple. Many of you now might lose track what job we were trying to do. We were simply turning on and turning off a certain pin or an LED that is connected to the pin at a certain duty cycle, right? So here we try to understand that how the control is flowing, right? If we started with something like this works gracefully, and we started something like with digital write, right? So this was the API, and we saw that what exactly goes underneath in getting this digital write to work, right? And if we are using digital write directly, so the extra overhead sort of hampers the speed of the code as well as the memory that is consumed in the final code, right? So there are lots of ways to shrink that code by doing this kind of jobs, right? So as much as you can be the close to hardware, the efficient your code will be. So this is the machine code. and if you can actually view the hex file that is generated, so the red portion that is colored here, that is a part of our code, right? The code that we have written, and the rest will be some boilerplate code for starting off a lot of different operations inside the microcontroller, right? Lots of things has to be initialized in the hardware itself, right? So those things are the boilerplate part, right? And apart from that, whatever code we have inserted is identified by this red signature here. And if we are using this direct register access, I have sort of marked out this code, whereas on the right hand side, if we use this APIs directly, right, the pin mode as well as the delay function or the digital write function, it actually adds to the overhead. And instead of, if you remember, this was something in the order of 460 bytes or so, whereas this was something 900 plus bytes, right? So that extra overhead is because of this API calls and so much of the function calls, right? And that slows it down, and also that adds to the space, right? And this is all about the machine code, right? So you see there is a whole lot of difference if we discount the boilerplate code. So from line number 27, this is where our code starts, right? Whereas it ends at 32, whereas in this case it starts from the same location and then it goes on till here, right, achieving the same task. And finally, today's idea was to basically give you the overhead of all this abstraction that takes place in microcontroller programming, because any of these IoT systems is going to be running at real time, right? So most of the operations has to be written very efficiently, using as little space as possible in the application flash memory, as well as with respect to time, right? We want to maximize the resources that we have in the hand, right, the hardware, right? So one example I was showing you was to just generate a square pulse, right, by turning off or turning on a particular pin. Even doing something as simple as that at a higher frequency was not possible because of this abstraction overhead, right? And there was this series of or the spectrum of abstractions that I mentioned, because at every individual higher level, one more abstraction is added, right? And I have actually shown you the bare metal programming, the way it is called, directly interacting with the underlying hardware, right? So we already know the hardware address, and we were like different registers address, and we were manipulating the addresses directly, right? We are manipulating the content directly, right? So it's something close to what is called bare metal programming. And then we can go all the way, right? Somebody can write more APIs using the existing APIs, right? For example, we have this digital write function, we have this delay function, and out of combining them, somebody can write a function called blink LED, right? So I can write a library that will have something called blink LED, and you can mention the pin number, and let's say that you mention the duty cycle, right? Let's say 500 milliseconds. Okay, so you can give a LED library that has this high level API, right? So there is it is adding one more level of abstraction, right? And you'll see the code basically becomes more and more inefficient, and it takes up more space and so on, right? So once you understand your necessities, what you really want to achieve out of the code, you have to somehow make the code as slim and trim as possible, right? Whatever is not needed in your application, you should not waste your precious application memory in storing those kind of data or storing that kind of code, right? So with this I'll conclude. So next class we will start a little bit on the sensing side. We will again come back to the microcontroller or the programming part, right? We won't visit the architecture part per se, but some of the programming part will be revisited as we sort of discuss different aspects of sensing. For example, when we discuss quantization, ADCs, we are again going to implement that, right, and show you how it works in practice. So we will wrap up today's class. So we'll see you soon in the next class. Thank you.